Hey guys, so today we're going to be starting a new lesson 7.4 for determining chemical formulas. So basically what we're going to be doing in this lesson is we're going to use our concept of moles and percentage composition and everything that we've already learned in order to determine the actual formulas of certain compounds, right? So the first thing we need to talk about are empirical versus molecular formulas, okay? So basically, an empirical formula is the simplest form that a formula can take. So if you look over here, you'll see this right here. CH is the empirical formula. When I have this unit, or multiplied by 2 or 3, like let's say here, this is CH times 2, so C2H2. At its base, it's still CH in its simplest form, but as soon as you turn it into this, you multiply it by a certain number, you end up getting the molecular formula. Now the empirical formula is just a representation of these simplest whole number ratios. But this is not the actual formula of the compound that we're talking about. So if we're talking about here, like acetylene, this is C2H2. Benzene has the same empirical formula as acetylene, except it's C6H6. So here, acetylene is 2 times the size of its empirical formula, while benzene is 6 times the size of the empirical formula. But in the end, both of them are a C1 to H1 ratio, 1 to 1. All right, so I'm sure you guys remember that in general, we use empirical formulas to represent ionic compounds, right? Because basically ionic compounds are found in these large crystals, right? And you'll have so many different ionic compounds all together. So instead of representing like N2Cl2 or N100Cl100, it's just always represented as NaCl, right? We go for the simplest form, and that's the empirical formula. But when it comes to molecular compounds, we will rarely represent them using their empirical formulas. We need the actual molecular formula. And the molecular formula of a compound is going to be the actual number. So you see this, B2H6. This can be simplified to BH3, right? And then that would be the lowest whole number ratios that they can be in. But because it's molecular, we're representing it by its molecular formula, not its empirical formula. All right, so here are just some examples of empirical versus molecular formulas. So you can see H1O1 can be turned into H2O2, and that would give you hydrogen peroxide. Sometimes the empirical and the molecular formula are equal. So in the case of water, this is the simplest form that it can take, 2 to 1. And this is also just the formula of water. It's not going to turn into H4O2. That's just not going to happen because that's not what water is, right? All right, and I'm sure there's another example here. Ethanol is also, its empirical formula is the same as its molecular formula. But in almost every other one of these, you can see that this was multiplied by a certain number to give you the molecular formula. So empirical is the simplest form. Molecular is the real form of a molecular compound. All right, so let's go ahead and try some examples here. I can see here that I have my molecular formulas and I want to turn them into empirical formulas. Now this is a lot easier than it seems. All you need to do is find a common factor between all the numbers in your formula. So I can see here that 4, 2, and 8, they can all be divided by 2 to give me a simpler number. So let's divide this by 2, and this by 2, and this by 2. That would give me H2, S1O4. Remember, we don't usually write the 1 here, so it's just going to be H2SO4, which ends up giving me sulfuric acid, right? So this is the simplest form that it can take, and this is the empirical formula. All right, Now, let's try this one. This is a sugar molecule, C6H12O6. Let's try to divide each one of them by 6 because they're all divisible by 6. 6, 6, and 6. We'll end up getting C1H2, because 12 divided by 6 is 2, O1, which will end up giving us CH2O, right? So there we go. That is the empirical formula for sugar. Let's find the empirical formula for iron chloride. Remember, this right here is ionic, which means it should be represented by its empirical formula. So this is actually not the best scenario for it to be in. But basically, what we can do to turn it into its empirical formula is find a common denominator, or something that they're both divisible by. So let's try to divide each one of them by 2 and see what happens there. So Fe1, because 2 divided by 2 is 1, Cl3, because 6 divided by 2 is 3. This will end up giving me FeCl3. That's its empirical formula and pretty much the best way to represent an ionic compound. The remaining 2 are molecular, which means they have covalent bonds. So these 2 would normally not be represented in this way, except for this one, because this is actually its correct formula. All right, so now let's try instead to turn our empirical formulas into molecular formulas. So basically, there is a connection between their masses and their formulas, right? So if I take an empirical formula and I know that its molecular formula is 2 times heavier than the empirical, all I need to do is multiply the empirical formula by 2 and I'll get my molecular formula, because I know that it's 2 times heavier, which means that there must be 2 of everything inside of it, right? So let's say here the molecular formula has a mass 2 times greater than that of the empirical formula. Okay, so HO, let's multiply this by 2. Each one of these has 1, so we end up getting H2O2, because we multiply this by that and this by that. There we go. So this is our molecular formula. Remember, the molecular formula here is 2 times heavier than the empirical, so this actually makes sense. And if you did your molar mass calculations, you would see that this one's molar mass is half the size or half the mass of that one, right? So let's try another example. Let's say C2H4O. This one, our molecular formula is 3 times greater than the molar mass of the empirical formula. So let's go ahead and do 3 times C2H4O. Multiply 3 by 2. It'll give you C6. Multiply 3 by 4. It'll give you H12. And then multiply 3 by oxygen. It'll give you 3 oxygens. So there we go. That's our molecular formula. And if you actually went ahead and did the math, you would see that this molecular formula is 3 times heavier than the empirical formula. Okay? All right, and now let's try the last one. Here, this one is 2 times greater. The molecular formula has a mass 2 times greater than the empirical formula. So let's go ahead and put it out here. SCl, sulfur and chlorine. Let's multiply this by that and this by that. Remember, each one of these is represented by 1, which means we have 1 sulfur and 1 chlorine. And we end up getting S2Cl2. There we go. That's our molecular formula. See, very simple. All right, so now guys, you have a quiz on Google Forms. You can go ahead and work on that. Good luck.